Okay, so today we're going to discuss periodic trends. Two of them are discussed in the beginning of the chapter, and then the third one we're going to talk about, electronegativity, is discussed within the bonding section. I've always thought it was better just to get them all done at once. The first thing we're going to look at is something called atomic radius. It's got a much more elaborate definition than just the radius of a circle that you'd have in geometry. The definition is 1/2 the distance between adjacent nuclei. For this to work, these nuclei, or the element we're talking about, has to be in the solid state so that the atoms are as close as they can possibly be. So if we have some atoms, nice circular atoms like I always draw, and I mark the nucleus in each one of them, you take the distance from there to there, cut it in half, or the distance from here to here and cut it in half. That is the definition of the atomic radius. So after you take your notes, I want you to think about this. Think about why we have such an odd definition of a radius as opposed to half the diameter. Okay, so we're going to look at the trends. We're going to look at going across a period from left to right, and we're going to look at what happens when you go down a group. Now, interestingly enough, and sort of very counterintuitive, is the fact that the radius gets smaller from left to right. Okay, and if you're thinking, you should be thinking, you're going, okay, we're getting more electrons. As we get more electrons, this radius should be getting bigger. Why is it getting smaller? You're also getting more protons. And these electrons can't go zipping out to the next highest orbital, so they're stuck in the same region of space while the pull from the nucleus gets tighter and tighter. And so when you go across, the radius actually gets smaller, even though you're adding more protons and more electrons to that particular atom. So the reason this is happening is we have more protons pulling in on the electrons. The only weird one you have to remember. Next, we're going to look at what happens if you go down a column. Okay, as we're going down a column, n, the principal quantum number, gets bigger. Whoops, that says bigger. As n gets bigger, that means the orbitals get bigger, right? And as the orbitals get bigger, that means you're going to have larger radii. So as we go down, the radii increases. As opposed to up here, going across from left to right, we see a trend towards smaller radii. Now, if we draw just a rectangle as a periodic table, because, hey, I can almost draw a rectangle, you have this overall trend of elements getting larger, at least in terms of their radius, going from right to left, and larger going down, with an overall trend, a diagonal trend of them getting larger going to the bottom left-hand corner. Okay, so that would be your trend in atomic radii. Whoa, handwriting is getting bad. Okay. The next thing for right now is something called ionization energy. Okay, ionization energy. We're obviously going to be making an ion of some sort. And this is defined as the energy needed to remove, oops, an electron from a gas phase atom. Again, this is another think about it kind of deal. Why does this have to be in the gas phase? Why gases? What would happen if you started with a solid or a liquid? I mean, most of the elements are solid. What happens if you're putting energy into those? What's going to happen first? Are you going to be pulling electrons off? I don't think so. We will come back to that in a discussion in a bit. Okay, so what do you know about electrons? Electrons are going to be held more tightly to smaller atoms. Okay, that's because the pull from the nucleus is going to be stronger for those smaller inner shell electrons, or just smaller electrons. So what we're going to find is as the atoms get larger, the ionization energy is smaller, and as the atoms get smaller, the ionization energy is in fact larger. But before we do that, the book talks about defining 3 types of ionization energies. You can take away more than one electron. So say you have atom X, and atom X is in the gas phase. That's what the little sub G is for. And you put in energy, you are going to produce an X plus gas phase cation and a free electron. So that electron, that's a negative sign there, that electron is floating away. It's been separated from element X. So you've got a cation and this free electron who can do whatever it pleases. Okay, that is called the first ionization energy. I don't have room to write ionization energy in here, so I'm just going to write IE, ionization energy. Okay, take this guy, this X plus 1 cation. Still in the gas phase. If you add more energy than you added the first time, more energy on an absolute scale, just not more energy than you already put in, you're going to get an X plus 2 cation in the gas phase and another free electron. That's called the second ionization energy. Okay, let's take a look at the third ionization energy. We've taken that plus 2 cation, and you suppose it's still in the gas phase. Suppose it's going to take more energy or less energy than these other two. Well, we haven't removed any protons. You've got the same pull from the nucleus in each case, and as you might expect, that pull from the nucleus is going to be stronger as you reduce the number of electrons. So this is going to be even more energy, giving you an X3 plus cation in the gas phase and another free-floating electron off there doing its business. Okay, so this is going to be the smallest amount of energy. That's going to be more. That's going to be even more. So say if this was 10 joules, this would take 25 joules. This may take 50 joules. These numbers are totally made up, but I'm just trying to give you a sense of bigger. Looking at our good old rectangular periodic table one more time, ionization energies are going to increase this way. Okay, towards a smaller element. They're also going to increase going upward towards a smaller element. Or you're going to see a diagonal trend going to the upper right-hand corner. We're going to practice with a few examples in a while.